So I want to thank the organizers of this conference for the opportunity for me to come here and share this presentation. It's titled A Brief History, and the idea is to provide some context for the detailed science talks that you're going to be hearing over the rest of the day. Because in terms of Western science, we didn't just get here a couple of years ago or 10 years ago or so on. There was some important work from generations past that took a while to get passed on, but once it did, that dialogue became really important. And so I'm going to talk a little bit about some of those early studies, including the establishment of the first carbon dioxide monitoring station in 1958, the first climate change projections, the importance of doing assessments, and you heard that I worked for the IPCC as well as national assessments. Well, these assessments they're snapshots. So you get author teams brought together, and they're asked to review all available information to date and create a snapshot and distribute that information around the world. And that became really important because it led to the communication of consensus and enabled governments and hopefully people to act on it. So let me start with this person. His name is Svante Arrhenius. He's from Sweden. And yes, that's, if you can read the top of the article there, you'll see the date is April 1896. Yes, there were a few scientists that were noticing the Industrial Revolution starting, coal burning, lots of emissions. And he asked this question: if coal is burning, that means there's carbon dioxide and it's getting the atmosphere. So what would happen to the climate if carbon dioxide increased in concentration? And in his paper, well, he did a few calculations by hand. There were no computers. And he determined that if carbon dioxide was to double in concentration in the atmosphere, the world would warm somewhere between 1 and 4 degrees. Well, for decades after that, a few people were working on this, but then you had World War I, and then you had World War II. There wasn't a lot of interest in climate change. But after the Second World War, a new generation of scientists, they started to look at some of the old papers and said, we really need to pay more attention to this. And one of the things we need to do is measure CO2. So along came an American named Charles Keeling, who established a carbon dioxide monitoring site in Mauna Loa in Hawaii. And he picked that place because he wanted an observing site that was far away from big cities and industry. He wanted to see if the atmosphere as a whole was showing a change in CO2. And so this graph on the bottom here, this one, was included in this paper he published in 1963, and it shows a definite increase in CO2 over the previous 3 years, from about 313 parts per million to about 315 parts per million. That publication led to others wanting to track CO2 and its effects on climate. So this report came out in 1971, and it's called Inadvertent Climate Modification. Why inadvertent? Because this is not happening on purpose. This is a byproduct of billions of people and millions of businesses and thousands of communities and hundreds of countries just using coal, oil, natural gas as part of their everyday life. To travel, to manufacture something, to farm. This is a byproduct of all of that. That's why they called it inadvertent climate modification. And there's this graphic here, which was a projection of CO2 from the 1970s to the year 2000. And the projection was, if CO2 keeps increasing at this rate, then by the year 2000, CO2 will increase from 315 to 375 parts per million. So that's one of the results of that report. But that's still just CO2. What about climate? Well, during that time, you began to see the first modern computers. Computers becoming more and more powerful. So it offered an opportunity. Instead of sitting at your desk and trying to do a few dozen calculations by hand, imagine being able to do hundreds of thousands of calculations by machine. And that led a few scientists who were thinking about climate to come up with the first generation of global climate models, mathematical expressions of how heat and moisture are transferred in the atmosphere. And this person was one of the first ones to do this. His name is Syukuro Manabe. He worked at the Geophysical Fluid Dynamics Lab in Princeton, New Jersey. And his model, he ran a scenario, again, 2 times CO2. What would happen to the temperature if CO2 was to double? And his model run determined that the world would warm around 3 degrees. A few others started to get involved, and that led the US National Academy of Sciences to convene a panel and said, we need an assessment of the information available to date. Find all the literature you can and boil it down to clear, concise statements about what we know and what we don't know about carbon dioxide and climate. So this assessment came out in 1979, and the conclusion at the time was, if CO2 doubles, temperatures will increase by 3 degrees, plus or minus 1.5. That first assessment became quite widely distributed in the science community. And during the 1980s, not only were climate scientists getting involved, but so were a whole lot of others. Agriculture, forestry, ecology, engineering, coastal zone issues, public health. The broadening out of that conversation led to a huge increase in literature, the attention of governments, and ultimately the attention of the United Nations. And in 1988, the IPCC was formed by the United Nations. We are celebrating this year the 30th anniversary of the IPCC. And its purpose was to provide policymakers with regular assessments of the scientific basis of climate change, but also the impacts, future risks, and options for adaptation and mitigation. So this is not just about climate. It is about the breadth of the issue, all the disciplines that are relevant, all the scales that are relevant. So this goes way beyond just atmospheric science. And over the years, the IPCC has become a very key source of information on climate change. These are the 4 volumes of the 5th assessment that was published in 2013-2014. So each volume is specializing in a particular aspect of climate change. The climate, the impacts and vulnerabilities, the energy issues, and the last volume is a synthesis report to look at questions that combine all 3. And it's important to point out that the IPCC itself is a very small office. The ability to create these assessments depend on volunteers. So when the call goes out for a new assessment to be created, all the countries that are interested in this start canvassing universities and other scientific bodies in each country to find people who are willing to volunteer to be part of an assessment. So these massive lists of names get sent off to the IPCC, and author teams get organized. And every few years, that's what you have, is volunteer author teams organized to write on their specific specialty to create these products. And these products get reviewed a lot. They'll go through 3 or 4 rounds of review each time. And so these are seen by governments and by the world as a whole as authoritative, as value-added, and as policy relevant. Relevant, not prescriptive. The IPCC will not prescribe what specific thing a specific country should do, but the hope is that science will enable decision-making by all countries. So similarly, the government of Canada has been carrying out national assessments. We've been doing this since 1998. These are 3 reports that came out more recently, 2008, 2014, and 2016, led and coordinated by the Department of Natural Resources, and they're all available on the NRCan website. Let me turn to a couple of global scale climate indicators, again, just to set up the context for where we are. Remember Keeling's original CO2 measurement, 315 parts per million. Well, this graphic up here shows a continuation of the Mauna Loa record to the present, and we're sure not at 315 anymore. We're at 410. CO2 has increased by 1/3 in 60 years. And this is because billions of people, millions of businesses, thousands of communities, hundreds of countries, all using fossil fuels as part of their everyday life, as part of their everyday economy, having this side effect on the atmosphere. But that huge increase is even greater when you look at it in the context of hundreds of thousands of years. So this record here, this jagged line, is based on ice cores that have been obtained from Antarctica. So scientists, they extract huge cores of ice and they slice them into layers, they date them, and then they extract little gas bubbles to see what percentage of that is CO2. And so over 400,000 years, you see the fluctuation of CO2, but never in all that time was CO2 above 300 parts per million. So we are living in an atmosphere now where CO2 is higher than at any time in the last 400,000 years. So that's the present. What about the future? This gets really tough because it's pretty hard to predict behavior of people and behavior of businesses and behavior of bright minds that invent new technologies. This is not climate. This is predicting energy futures. So we rely on now a different group of people who have expertise in energy technologies, in how energy is being used by a wide range of businesses, transportation, manufacturing, and the like. And also contributing to this are people who are thinking about population, demography. What are the population growth paths for different countries around the world? And so there's a series of pathways here. They're all called RCP, which stands for Representative Concentration Pathway. The higher the number, the greater the emissions, the greater the amount of heat trapped, and ultimately the greater the temperature. We're on this path here, pretty darn close to the red one, which if we continue along that way, we'll end up in RCP 8.5 world, which would mean a warming of potentially 5 degrees. However, if we could create an environment where low carbon technologies are used widely, like wind and solar and so on, we could see CO2 emissions decrease. We would be in the RCP 2.6 path, and maybe we would only warm by 1.5 to 2 degrees. That would be very different from a warming of 5 degrees. What we are fairly certain about is that the warming we've seen already over the 20th century, it's unequivocal. It's not some artifact of stations being in the city. This is worldwide, and we have warmed, and it's largely because of greenhouse gases. And continued emissions of those gases will cause further warming. But what will that mean to people? And for that, again, we have to turn to others who are experts in food production, in ecosystems, in fisheries, in forestry, in coastal zones, in engineering, in public health, in insurance, to determine how this warming will change risk. We all deal with risks today, all the time. The question is, will climate change make a difference to future risk? And so this graphic that appeared in the last IPCC report combines the temperature projections from the climate community, with risk projections from the impacts and adaptation community. And you have these 5 red bars here. Red means high risk, yellow means moderate risk. And this collection of information that was being looked at by the group that created this diagram, they tried to figure out, well, where's the boundary between moderate, yellow, and high, red risk for different indicators. So the one on the left, unique and threatened systems like coral reefs. The second one, extreme weather events, floods, droughts, hurricanes. The third one, distribution of impacts. The ones most vulnerable may be hit first, like a small island state, but at what point are we going to see impacts beyond small island states and covering more and more people and places? Global aggregate impacts, species at risk around the world. At what point will we see at a global scale greater and greater species at risk? And finally, large-scale singular events like the collapse of the Greenland ice sheet. Now you see where yellow meets the red, and compare it on this scale to the right, it's somewhere around 2 degrees. And at the bottom, I've indicated in words, at 2 degrees, risk is rated at moderate to high for all 5 indicators. But if we were to warm to 4 degrees, risk would be rated high to very high for all 5 indicators. That's why 2 degrees is in the Paris Agreement. That number didn't come from a dartboard. It came from this very extensive assessment of available literature and also, of course, the expert judgment of the people that created that graphic. But this was not a trivial exercise. And in the end, they concluded that we're going to see at 2 degrees an increase from moderate to high risk for a whole lot of things that we care about. So 2 degrees is in the Paris Agreement. But that's not the only thing that's in the Paris Agreement. Article 4 says we aim to reach global peaking of greenhouse gas emissions as soon as possible, recognizing that that's the cause. But don't leave adaptation out because we still have to adapt to those risks that are coming. So Article 7 says we establish the global goal on adaptation based on and guided by the best available science and traditional knowledge, knowledge of indigenous peoples, and local knowledge systems. That's written in the agreement. And this agreement has been signed by 190-something countries. In Canada, there are a couple of things that both the previous government and the current government did. One was to add greenhouse gases to the Canadian Environmental Protection Act in an amendment a few years ago. The original act did not have methane and carbon dioxide. The amended act does. And in 2016, the current government established this pan-Canadian framework on climate change in a series of negotiations with, well, almost all provinces. And that framework is still developing. But it's not just governments. It's also people in business, finance, insurance, banking. They've been noticing this too. And every year, you've probably heard of the World Economic Forum. They meet, I think, in Davos, Switzerland. And they produce this document called the Global Risks Report. And this is the most recent one from 2018. So this diagram here is a risk diagram. So the vertical axis is impact, the impact, magnitude, consequence. And the horizontal diagram is likelihood. How likelihood is it to occur? So the worst case risks are the ones that are on the upper right of that diagram. And this diagram was based on surveying several hundred people from the banking, finance, insurance sectors. So these are not scientists, these are people in money, business. And the top 3 global risks identified by that community is extreme weather events, natural disasters, and the failure of climate change policy. The finance world sees global climate change, human-induced global climate change, as a bigger risk than cyber terrorism, than weapons of mass destruction, than interstate conflict. Why? Because they see it as a risk to all normal business and economic transactions. They see it as a threat multiplier to the normal day-to-day things that countries and businesses do. So they rated it as being very high. So to conclude, we got here because many generations ago, a few scientists asked a question and started doing some work on it. A few generations after that, some other scientists revisited what they said, and they said, we really need to pay attention to this. So from Arrhenius to Keeling, until finally to Paris. So learning started decades ago, but more recently knowledge sharing expanded, and it was aided by these assessments, the American assessment, the Canadian assessment, the IPCC assessment. These snapshots were really important to get the word out beyond the research community. And so as a result of that, we have acceptance of science findings by governments. We have the Paris Agreement signed by 197 countries, which brings us to this event here. These events are just so important for knowledge sharing and for enabling evidence-based decision making, for bringing that global scale issue down here to the community. Thank you very much.